Okay, in this experiment conducted by JF Chem teacher on YouTube, okay, what happens is you have a beaker of ice, okay, pure water, ice, right, that's being heated up by this machine here. So this machine is constantly supplying heat to this beaker of ice until it melts, becomes water, and then it starts to boil at 100 degrees Celsius. So the question is, how do you expect the temperature of this substance, this water, to actually change with time? Right, since most of us will probably think that, okay, since heat is constantly being supplied to this ice, it will increase in this way, straight line or curving upwards, increasing gradient, or increasing but with a decreasing gradient. But that's not what actually happens. Let's take a look at the experiment. Okay, so at 0 degrees Celsius, what you observe is that even though heat is being constantly supplied to the ice, you realize one thing, that somehow the temperature does not increase. Alright, we continue observing, right? Yup, the experiment, JF Chem teacher said that heat is being added to the water, but the temperature is not changing. It remains at 0 degrees Celsius. Okay, later on at 50 degrees Celsius, okay, after the ice has melted, okay, the temperature constantly increases, steadily increases all the way. Okay, but then you start to realize that the temperature increase has slowed down a little bit when it's approaching the boiling point, which is 100 degrees Celsius. When it reaches 100 degrees Celsius, what happens? You notice that at this point here, at the 100 degrees Celsius mark, okay, temperature is not increasing. Even though the water is boiling, you can observe the bubbles. Right? Heat is being constantly supplied to the water, boiling it, but the temperature is not increasing. Why is that so? Alright, so we will explore and explain this in this chapter. Hey guys, what's up? Welcome back to the classroom. It's Mr. Low, and today we'll go on to the next chapter, chapter 9, thermal properties of matter. Right, so in this chapter, we will mainly try to explain the heating curve that we saw just now. Why is it that at certain temperatures, at 0 degrees Celsius and 100 degrees Celsius, the temperature of the water did not increase even when heat energy is being constantly supplied to the water? Alright, so we try to explain that by looking at the molecules, by zooming into the molecules of the substance, in this case is the water, alright, and try to explain why is that so. Alright, so without further ado, let's get into it. But before we begin, before we zoom in to look at the particles, let's do a little recap, you see. Okay, so we do recap that everyday objects, like a ball, your tables, your chairs, yourself, your own body, right, can have two different types of energy, namely kinetic energy and potential energy, right? So you can have kinetic energy and potential energy. Particularly, what kind of potential energy that we have been talking about? Looking at this picture, okay, we have been discussing gravitational, right? Gravitational potential energy. Gravitational potential energy, or GPE, right? Okay, so recall a little bit, all right? KE is due to the object moving. So any object that's moving should have KE, and any object that is at a height of the ground should have some form of potential energy, namely gravitational potential energy, right? And then we recall a little bit that particles, right? If we recall from chapter 7, particles in a substance, let's say a solid, right? They are constantly moving. For example, particles in a solid, they are vibrating about fixed positions, right? So these guys, they are vibrating, right? So this is the previous chapter, right? The fact that they're vibrating or they're moving means that they possess some form of kinetic energy, isn't it? Because they're moving, all right? So we try to relate the energy of the particles in this chapter, right? So recall that particles have internal kinetic energy. Okay, I'm going to emphasize this a little bit in this video, right? When we talk about particles, the energy possessed by the particles in a substance, we use the word internal. Okay, I'll explain why we have to do so. Okay, so particles have internal kinetic energy and internal potential energy, okay, due to some form of intermolecular bonds. And then these particles, because they have internal KE and internal PE, the sum of these two energies give rise to the internal energy of the particles in a substance. Okay, so this is the success criteria for this part. Okay, internal KE, let's get right to it, right? Okay, so as I was saying just now, right, particles, be it in solid, liquid, or gaseous state, they are always in constant random motion. And the fact that they are moving means that they possess some form of kinetic energy, right? And we call that internal kinetic energy. I'm going to emphasize that you need to write the word internal for particles, as opposed to everyday objects. Like a moving car has kinetic energy, but the particles in the car that makes up the car have internal kinetic energy, right? So we emphasize that because we want to differentiate or distinguish between the kinetic energy of the particles inside a substance, like in this case a solid, and the kinetic energy of the whole solid, you know, if it is moving, you see. So the whole object as it's moving, it has kinetic energy as a whole. But when we zoom into the particles, right, the particles are vibrating at their own fixed positions. They have kinetic energy also. So we call that internal kinetic energy, as opposed to the usual kinetic energy of the object that we can actually calculate. Alright, so just bear in mind, I will be using and emphasizing on the word internal when we talk about the energy possessed by particles in this chapter. Okay, so we also remember that, okay, as the temperature of the substance increase, the particles move faster. So this part here is chapter 7, also discussed in chapter 7, kinetic model of particles. Okay, if you forget, just do a quick recap. Okay, so what is happening in terms of the energy here? Okay, so when we heat up a substance, right, okay, we have input of thermal energy into the substance gains thermal energy, all right, and it's being converted into internal kinetic energy. Okay, so recall this is the conservation of energy, right? The law of conservation of energy. Energy cannot be created nor destroyed, but can be converted from one form to another. So in this case, all right, usually, under usual circumstances, we give the substance, you know, thermal energy, right? The particles absorb the thermal energy and then it gets converted into internal KE, right? So at the microscopic level, when we zoom in to look at the particles itself, because they gain internal KE, right? Internal KE increases, what happens? They actually move faster, right? Because, well, higher the KE, the faster the object is moving. But in this case, we're talking about the particles, okay? And then from there, what do we observe, right? We observe that as a whole, because we can't really zoom in and look at the particles move faster, but what we can observe actually is that temperature increases. This is what we can see. But particles moving faster, this part is something that we cannot see, you see. All right, so this is the flow of events, what's happened, right? So thermal energy increases, internal K increases, the particles move faster, and as a result we see that the temperature of the object as a whole increases, right? We don't measure the temperature of the particles, right? And then on the other hand, right, if we were to cool the substance down, right, the opposite happens, right? Okay, thermal energy is being lost from the substance to the surrounding or to the freezer or whatever, right? So this loss in thermal energy is due to the loss in internal kinetic energy of the particles. So in a way, you can say that the internal KE of the particles gets converted into thermal energy, and that thermal energy is lost to the surrounding when it comes to cooling process. Okay, so since the particles lose internal KE, what happens to their motion? They move slower. Okay, yeah, so you lose KE, you move slower. Okay, now of course, again, we don't observe the particles moving slower. We can't see that, but what we can actually see is that the temperature decreases of the substance. The temperature of the substance as a whole decreases. So from there, we kind of infer that, you know, energy is lost in a way, right? So now what we're doing here is we are trying to relate heat energy to how the particles move, and then we relate it to the temperature of the substance as a whole. Okay, so some practice question here. Comparing solid, liquid, and gaseous state of the same substance, in which state do the particles have the most internal Ke? Right? So for that, you have to recall a little bit what is the motion of the particles in the three states. Right? So for solid, particles vibrate, right, about fixed position. For liquid, the particles, slide past each other, right? They are kind of free to move and they slide past each other. And for gaseous state, what happens? They move freely and randomly at high speeds, right? So move randomly at high speeds. Yeah. So looking at these keywords, right? Vibrate, slide past, high speed, it's quite clear that particles in gaseous state actually move the fastest, right? This one, I think we're already quite familiar with that, and very clearly, right, because the particles are moving at a higher speed in gaseous state, then we know that the particles have the highest internal Ke when it comes to comparing solid, liquid, and gas. Alright, so the answer is the gaseous state. Sorry, you should be writing gaseous instead of gas state. Gaseous. Gaseous state, right? Because the particles move the fastest among these three states. Okay? And we know that the faster the particles move, the higher the internal Ke they have. Alright, so this part is quite easy. We're trying to relate, temperature to the energy and the movement of the particles. Next, this part is a little bit abstract. Okay, see if you can understand, right? Now, previously, we say that, okay, we know that the particles are moving, always, right? So they have some form of kinetic energy. We call it the internal kinetic energy. Now, some things that we cannot really see, but we know that it's there, is that between the particles, there's some form of forces of attraction. Now, if your notes, if it's stated bonds in the notes, please cancel and change to the word forces of attraction. Right, now there's some things, there's this thing called forces of attraction between particles in a substance, right? It's sort of like a invisible rubber band, as I'll call it. Okay, so imagine, right, let's say this is a solid state, right? Okay, so imagine this particle and this particle here, they are bonded together, they're held together by a mysterious rubber band. Okay, so they are kind of tied together. All right, we call this the forces of attraction between the particles. Okay, so how does this give rise to some form of potential energy? If you think about it, right, rubber bands, if you stretch rubber bands, what energy do you get? Well, some of you may know that we actually get elastic potential energy. It's a form of potential energy as well, right? But for the case of the rubber band, it's elastic, right? But in this case, because of this intermolecular force of attraction that behave like rubber bands, right? These particles have internal potential energy, right? I repeat again, in the same way as the rubber bands, when you stretch it, they possess elastic potential energy. So this force of attraction give the particles the internal forces. The internal force of attraction give particles the internal potential energy. Okay, so again, right, internal because we are talking about the particles now. Okay, so how does this internal potential energy actually change? Okay, now let's recall a little bit. Again, back from chapter 7, when the particles when the substance melts or boils, when there's a change in state, right, melting or boiling, we recall that the particles actually move away from each other. Okay, so for example, from solid to liquid, the particles, the arrangement of the particles change from fixed orderly position to slightly far apart, right? Are closely packed to slightly far apart, so they actually get further from each other. Now, when the particles try to get further from each other, let's say like this, okay, what happens to this rubber bands over here? Well, we don't call it rubber band, we call it forces of attraction. What happens to these forces of attraction here? Yeah, maybe you get it correct, they get stretched, you see. So if I were to try to draw the particles further apart from each other randomly, you can see that the length of this forces of attraction, they are actually further away from each other, right? Actually, each particles, they are kind of bonded to each other by all these forces of attraction, right? So you can see that it gets stretched, you see. So just like rubber bands being stretched, there's more elastic potential energy, right? Okay, so in this case, as the particles move further away from each other, okay, they overcome. Now please use the correct keywords. I've been talking about stretching, but it's for rubber band, so don't use the word stretching, use the word overcome. Right, so the particles are trying to overcome the forces of attraction, okay, interparticle forces of attraction. As a result, the internal potential energy increases. Okay, so I repeat myself again. During the change of state, you have melting or boiling. Okay, what happens is the particles move further apart from each other, and as a result, they try to overcome this forces of attraction, and as a result, this gives rise to the increase in internal potential energy. All right. So I hope this paints, by using the rubber band as an example, I hope this paints a clearer picture of how the thing works, okay? Now, you might have recalled something like this, learning something like this in chemistry. There's a little overlap here, okay? Now, in chemistry, there's a difference in the words, the keywords that we use, right, between physics and chemistry. Just take note, but we're actually talking about the same thing, right? So in chemistry, you might have come across this term called forces of attraction between the particles. In physics, we call it the intermolecular forces of attraction, which is kind of the same, right? It's just whether is it particles or is it intermolecular. Actually, we're kind of talking about the same thing, right? Later I'll emphasize a little more. For this topic, as I said, there's overlap between chemistry and physics. But we are actually focusing on different aspects of the same thing. Okay, so here's a quick summary. Alright, as the substance melts or boils, the particles move further apart, and as a result, internal PE increases. Okay, now at the opposite end, okay, the opposite of melting is freezing, right? Opposite of boiling is condensation. Okay, so as it cools down, as the substance freezes or condenses, during these two processes, the particles come closer together. Internal potential energy decreases. Okay, so do note that internal potential energy only changes during melting, boiling, or freezing and condensation. Okay, and the energy conversion here, we're talking about thermal energy to internal PE, or for the case of freezing and condensation, it is internal PE to thermal energy, and this thermal energy is lost to the surrounding. Okay, so next is you have internal KE and you have internal PE. When you sum up these two, you get internal energy. That's it. Okay, so one extra term, one new term, which is internal energy, which is equals to the sum of internal K and internal PE. That's it. Okay, here I'm making a comparison between everyday objects like a table and chairs and the particles inside these substances, right? So for everyday objects, you have KE, you have potential energy like GPE, right? And if you add up KE and GPE together, you get mechanical energy. Now that's something that we don't really need to know, but if you are doing engineering of any sort, okay, in the future, you will come across this term mechanical energy. For now, don't be too worried about it. Okay, now on the other hand, in contrast, particles, they also have KE, but we call it the internal KE. It also has PE, we call it the internal PE, right? You sum this up together, we call it the internal energy. That's it. Okay, so this part for internal energy is quite simple. All right, yeah, you may check out this video through the QR code. Okay, now we are going in with this concept, with this concept of internal KE and internal PE. We are now going in to try to explain the heating curve that we see at the start of this video. Why is it that at certain points at 0 degrees Celsius and at 100 degrees Celsius, temperature does not increase even when heat is being constantly supplied to the water. Alright, this is the big question, $1,000,000 question over here. Alright, so let's go through the success criteria. You should be able to explain the rise in temperature of a body in terms of gaining of internal KE. Right, so when you supply heat to the substance, most of the time its temperature is increasing. Right, and you explain by in terms of the internal KE. Alright, you should be able to sketch the heating and cooling curve, which resembles what we saw earlier. Okay, and explain in terms of the internal PE, why is it that there is no change in temperature when at 0 degrees Celsius and 100 degrees Celsius for water, even when heat is being supplied to the water. Alright, so let's carry on. Okay, heating curve. Okay, so at the start of the video I said that when you supply heat to the substance, most of us would guess that, oh, the temperature should increase in this way, or in this way, or the other way around, right? Okay, but we realize, like, by looking at the experiment, or if you do conduct the experiment yourself, you will realize that at certain point of the heating process, temperature does not increase, okay, at these 2 points. Okay, and if you're sharp enough, you realize that, hey, the temperature 0 degrees and 100 degrees Celsius correspond to the melting point and heating point of water. I hope you realize that. This is the melting point, and this is the boiling point. Of course, we are just talking about water here, right, of H2O. Different substances, their boiling point and melting point will be different, right? Okay, so yeah. Okay, so what is happening here, right? During the heating process, most of the time, like in processes A, C, and E, you realize that, okay, the temperature is increasing. That's quite common sense, right? That's quite common sense, okay? But the anti-climax part, right? The not so commonsensical part comes in when during the melting and boiling process, you realize that the temperature does not increase. Okay, and we have to explain why is that so. Okay, now, yeah, so D, B, and D are the melting and boiling processes respectively. Okay, it has everything got to do with the internal potential energy that we described just now. Okay, so there are a lot of words here, don't be afraid. Okay, I'll explain this in detail. Okay, so let's look at the first part, when it's melting. Okay, so during the melting process, the substance change from solid to liquid, right? So solid to liquid. Okay, now we're just looking at the solid and liquid part. We will go through the gas part later. All right, so well, the temperature starts from -15. By the way, solid ice can go below 0 degrees Celsius into the negative region. Okay, no problem with that. Okay, so assuming that we start off with a solid, okay, solid ice, okay, at -15, right? As we supply heat to it, okay, no problem, the temperature increases. Now, here comes the part, right? The exciting part. When it reaches the melting point, 0 degrees Celsius, you realize that the temperature does not increase for some time. Okay, so what is happening here? Well, we know that it's melting, but why is that so? Okay, now the reason is this: during the melting process, okay, so we focus on melting first. Okay, remember that the particles move apart. This is chapter 7. Okay, now just now we discussed that during this process, as the particles are moving further apart from each other, they are actually overcoming the intermolecular forces of attraction, right? As a result, the thermal energy gained by the substance is being converted to internal potential energy mainly. All right, so let's go back a little bit back to this picture here. As during the melting process, the heat supplied to the particles are being used to overcome these intermolecular forces of attraction. As a result, internal PE increases. This part here, right? Internal PE increases, right? So when when the thermal energy is being converted to internal PE, mainly what happens is there is no increase in internal KE. Okay, so heat supplied to the substance during this melting process is being converted to internal PE but not internal KE. Now, since internal KE does not increase, we realize that temperature does not increase, it remains constant. Okay, I hope this is clear. Alright, if you need, we will recall a little bit. Go back to the previous part and recall a little bit. How does internal KE affect the temperature? Okay, let me repeat again. How does the internal KE of the particles affect the temperature of the substance as a whole when we measure the temperature using a thermometer? Okay, so here is the difference between the focus of chemistry and physics. They're actually looking at different parts of the same phenomena, right? You might want to take this down. It's not necessary, but I thought that this is useful because the way that we phrase our answers in chemistry and in physics may be a little bit different. So just don't make sure that you answer, all right, the correct thing, because we're looking at different aspects of the same phenomena, right? If you would like to, you can pause the video and just take this down. All right, I'm gonna continue. Okay, so recap a little bit, right? During the melting process, thermal energy is converted to internal potential energy. Look at the green part here, right? Otherwise, during any other part, right, when there's no change in state, thermal energy is being converted to internal kinetic energy of the particles, and as a result, you observe that the temperature of the substance as a whole increases, right? So in part 1 and part 3 here, you see increase in temperature, but not part 2, because that's melting part, right? That's the melting process. Okay, so it's also true for boiling. I did not show the boiling curve over here, but it actually behaves at the same way, just that instead of 0 degrees Celsius, it's 100 degrees Celsius. Okay, so in physics, we are going to emphasize on the energy changes, the energy conversion. Right, so this table nicely summarizes what happens to the heat energy supplied to the substance during each stage of the heating curve, right? So the A, B, C, D, E in this table refers to this graph here. Okay, so let's go to the table here. For non-change in state process like A, C, and E, you realize that thermal energy is mainly converted to internal KE of the substance. This is why you see that the temperature of the substance increase. But on the other hand, for special cases like melting and boiling, what happens is the thermal energy is converted to internal PE as the particles try to overcome the forces of attraction. Okay, and as a result, because there's no increase in KE, there's no change in temperature. Pardon me, there's no change in temperature in this case. Okay, so I hope that is clear to you. Okay, we are mainly looking at these two special cases. Okay, the cooling curve is the opposite, right? You see that it is the exact opposite of the heating curve, right? Just kind of like flip it around, right? This is the heating curve, this is the cooling curve, right? Again, you see that, okay, during cooling curve, what you expect is the temperature should be decreasing all the time, but no, right? Temperature decreases for this part, but for these two special cases, G and J, you realize that the temperature does not change, and it actually has to do, it's the same explanation actually, just that the substance is losing heat energy instead of gaining, right? So you realize that, oh, these two temperatures again looks very familiar, right? It's actually the condensation point and freezing point. By the way, in case you forgot, the boiling point is equals to the condensation point, so you might want to take this down by the side. Boiling point equals to condensing point. Let's call it condensation point. okay, which is for water is 100 degrees Celsius. And on the other hand, the melting point is equals to the freezing point. Okay, melting point equals to freezing point. For water, in this case, it's 0 degrees Celsius. All right. So during these two special cases, G and J, okay, it is condensation and freezing respectively. So during these 2 points, again, temperature remains constant for some time. Okay. Okay. So what happens, right? What is happening there? How do we explain? Okay. So this is the freezing portion. Okay. But again, it works the same way for condensation. Okay, so for freezing, we have turning liquid into solid. Okay, liquid into solid. All right. So what's happening here? You see, okay, we start off at 90 degrees Celsius. For water, it's still liquid, right? Liquid cools down, no problem. So at this point, oh, sorry, this is a different substance. This is naphthalene. All right. Naphthalene has a freezing point of 79 degrees Celsius. Just take note here. Alright, so so you see the horizontal line, the freezing or solidification part at the temperature of 79 degrees Celsius. Alright, so what is actually happening here? Okay, during condensation or freezing, right? The internal PE of the particles are lost to the surrounding as thermal energy, right? So the what do you call it? The energy conversion is internal PE being converted to thermal energy, which is lost to the surrounding. Okay, so since the and this occurs because the particles move closer to each other, right? So they are actually overcome by the the interparticle forces of attraction, right? So as the particles come closer together, opposite of melting and boiling, right? They come closer together, they lose the internal PE, and the energy lost, the internal PE is lost in the form of thermal energy. Okay, so because the substances are losing internal PE but not internal KE, no decrease in internal KE, the temperature does not decrease, does not change. Okay, so you can see very clearly, right, from the two parts, from melting and this freezing example, you can see that the common thing is that if the temperature does not change, we know that the energy change is due to gain or loss of internal PE, and that there's no changes in the internal KE, right? Because once internal KE changes, the temperature will change. Okay, so again, this summary table nicely sums up the processes. Okay, so we are looking at special cases G and J, which is condensation and freezing. Okay, you notice that, okay, it is the internal PE that is lost to the surrounding. As a result, there is no change in temperature. For all other cases during the cooling process, like E, H, and K, alright, the internal K is the one that is lost to the surrounding in the form of thermal energy. As a result, there's a decrease in temperature of the substance as a whole. Alright, okay, now so with this, we have actually explained the heating curve that we saw at the start of the video. Okay, so let's recap a little bit. Why is it that when you heat up solid ice, you realize that at certain parts of the heating process, the temperature does not change? Well, it's because the energy, the thermal energy absorbed is mainly converted to internal PE. Alright, since there's no gain in internal KE, temperature does not increase. Right, the opposite is also true for cooling process, right? So in this case, for the cooling process, again, there are two stages whereby temperature does not drop. Okay, and we relate it to the change in state again, which is condensation and freezing in this case. And we know that, okay, the temperature does not change because the particles are coming closer to each other. They lose internal PE but not internal KE. right? So there's no change in temperature. Okay, now we come to the very last part, which is kind of related, but not exactly related to the heating curve. Okay, is the difference between, or rather the difference and similarities between boiling and evaporation. Okay, so some of you might have these two processes confused, okay, because both of them involve liquid turning into gas, right? So what is the difference between them? Okay, so we have to explain the differences actually, and remember the similarity between these two processes, and explain in terms of the internal energy, right? So this is when the concept of internal PE and KE come in, right? So in terms of the internal energy, why is it that evaporation causes a decrease in temperature of the liquid as a whole? What do I mean by that? Okay, when you have a glass of a container of liquid, okay, now as some of the liquid at the surface they evaporate off, what happens is the remaining remaining liquid, its temperature actually decreases when evaporation occurs. Why is that so? Okay, we will take a look by examining the energy, the internal energy of the particles. Okay, again we have to zoom into the particles to explain why. Okay, so first of all, look at this dialogue between Alice and Bob. Alice says, "Oh my god, I was sweating crazy just now. Luckily the sweat evaporated off very quickly." Actually, that's kind of a lie, because in Singapore the weather is very humid. Your sweat actually doesn't evaporate off easily, right? But assuming that this is another country, yeah? Okay, so Bob asks, evaporation means your sweat turns into water vapor, correct? Is that correct? Yes, answer is correct. Right, that's evaporation for you. Yeah, clearly Alice pays attention in class. Okay, now here comes the question. Bob asks, hang on, the teacher said that water boils at 100 degrees Celsius and sweat just turns into vapor on your skin. Does it mean that your body temperature is 100 degrees Celsius? Right, because, well, water turns into steam, right, or water vapor, right? So isn't that the boiling process? Right, so should it occur at 100 degrees Celsius since that's the boiling point of water? Well, clearly that's not the case, right? Okay, now, so clearly there is a difference between evaporation and boiling. Okay, so this table is for you to summarize what is the what are the similarities and differences between the two processes. So first of all, please take note that the very first three rows there are similarities between evaporation and boiling. So let's take a look. For both cases, for both processes, they both involve liquid turning into vapor or the gaseous state, right? Okay, in both cases, the liquid gains thermal energy when they turn into the gaseous state. Okay, and the thermal energy gains increases the internal PE of the substance. That is true, you know. If we look at the boiling process just now, the heating curve, right? Temperature does not change because internal PE increases, so on and so forth. Okay, so these are the three similarities between the evaporation and boiling processes. So what are the differences here? There are 1, 2, 3, 4, 5, 6. Okay, let me switch over to PowerPoint slides. Okay, by the way, if you recall chemistry, you may have learned this as kinetic particle theory under the topic of kinetic particle theory. Okay, so let me switch over to the slides here. Alright, here you go. Okay, so these are the differences. Okay, number one, boiling only occurs at a particular temperature. In this case, it's actually the boiling point. Okay, so you might want to write this down. Occurs at boiling point. Okay, but evaporation actually occurs at any temperature. You think about it. Okay, you hang your clothes out into the sun to dry, or even indoors. Right now, some washing powders actually allows you to dry your clothes indoors. Right, clearly, the temperature of the surrounding, whether is it outdoor or indoor, cannot be the boiling point of water, right? So in fact, right, it can occur at almost any temperature. Okay, now boiling is a fast process. You can see that, you know, the bubbles are being formed, you know, during the process. Very rigorous. It's a very fast process, but yeah, evaporation takes time. You see, to dry your clothes, right, you need to hang it outside for some time. Okay, and next, boiling takes place throughout the liquid. That means when you see that the bubbles are being formed, you know, and the water is actually boiling, you can see that boiling occurs at every single part of the container of the liquid. Okay, but evaporation only takes place at the liquid surface. Alright, so if you hang your clothes out, the outer layer of your clothes will dry out faster first, and then the inside. Okay, bubbles are formed, no bubbles are formed in the liquids. Okay, alright, temperature remains constant during the boiling process. We explained it just now, right? Because of the gain in internal PE, but not gain in internal KE. During the evaporation process, depending on how fast the evaporation is, the temperature may change. Okay. External thermal energy of the source is required, but for this evaporation case, external thermal energy source is not required. What do I mean by that? That means for boiling, you have to put it under a flame or some form of heater or whatever. But evaporation, it may just occur naturally, even though you don't supply heat to it. Alright, so these are the differences between these two processes. Do pause the video and take down the in your notes, okay? Okay, I'm just gonna move on. Okay, so now we have explained, or rather we have discussed the differences between these two processes, and for the last part here, okay, we need to discuss what happens during evaporation. Now, I'll start with this example here, right? We have all gone for a vaccination, hopefully, right? 2 jabs, and you know that for any injection, right, the nurse or the doctor would have swabbed your skin with an alcohol swab, and you realize that, hey, why is it that it's cooling? You know, when the nurse or the doctor applies the alcohol swab on your skin, that part feels cooling. Why is that so? Well, because it has everything to do with the with evaporation, right? The alcohol evaporates off your skin, right? So we'll explain a little why is it that this evaporation actually leads to cooling effect, right? The temperature actually drops, you see. Okay, so to understand why, let's look at the particles in a body of liquid, right? And we know that first of all, only particles near the surface, right, near the surface of the liquid will evaporate off and into gaseous state, right? So what happens in a liquid, but in a body of liquids, okay, there are some particles that have higher energy than others. Now, do not assume that all the particles here, or do not assume that all these guys, they have the same amount of energy. Okay, some of them might have higher energy than the others, slightly more. Okay, so what happens? These higher energy particles, okay, they make their way to the surface of the liquid. So let's say this guy here, originally, you know, it was here, right? So it has high energy, it wiggles its way up to the surface of the liquid. Now what happens? If they have enough energy, if the energy is high enough, they can so-called evaporate off. They can escape the liquid body and turn into gas. Okay. Now remember that there's this thing called intermolecular forces of attraction. So in order to escape the liquid body, to escape the rest of the particles, you must have enough energy to overcome the intermolecular forces of attraction. So that means these guys, when they have these guys who are so-called richer, right? They have more money. No, I mean more energy. Okay, they can escape off the water body, unlike the others. Okay, so this process is called evaporation. Now, how does this result in temperature drop in the liquid as the particles evaporate? Okay, now let's think about this. Let's think in terms of average, right? So remember, right, what is the meaning of average in mathematics? That means you sum up everything and then you divide by the number of data points, right? Okay, so now let's give you an example. Let's say we are talking about score, let's say math score, right, of the class, right, out of 100, okay, upon 100. Okay, so let's say we have like 5 students, right? Student student 1, 2, 3, 4, 5. Okay, and their scores are for example, you know what, let's just take 10, 20, 30, 40, 50. Okay, let's make it simpler. Okay, what is the average score for this bunch of students? Well, you simply add up, right? Okay, so I'm gonna calculate the average here is you sum up all, which is 10 plus 20 plus 30, that's 60, plus 40, 100, so 150, right? The average here is 150 over 5 students, that is 30. Okay, so this is the average score of the 5 students for this math for this math exam or math test. Now, assuming that the teacher says the highest scoring student gets to be promoted to the next level, right? But the rest must retain or take the exam again. Okay, so student number 5, being the highest scorer, can get out, just like this guy having the highest energy, the higher energy guys, they can get out. Okay, so assume that, okay, student number 5 with the highest score can get out of the class, or so-called evaporate off. Okay, now evaporate off. Now, what happens to the average of the remaining students? Okay, what happens to the average? So we sum up again. 10 plus 30 plus 40, that is 100. 100 over 4 is 25. Now, what do you realize here? After student number 5 gets out, or evaporates off, so-called, right? The average actually decreases. The average score actually decreases. Alright, so if we think of this as the energy of the particles, so instead of student, you have particles, and instead of scores, we have internal KE. Can you see why is it that temperature has dropped when the higher energy particles evaporate off? Right? So the answer is this, right? The remaining particles on average, they have lower energy because the higher energy ones have left, you see. So this is why, therefore, right, the temperature of the remaining substance, or rather the remaining liquid, will decrease. Okay, so I hope this math test example shows you clearly that how the average will change if you remove, right, the higher scoring students, just like how the average internal kinetic energy of the remaining liquid particles will decrease when the higher energy liquid particles have evaporated off. Okay, so let's think about this, right? When you go for injection, right, why is it that the alcohol side feels really cooling? Why is that so? Explain in terms of the thermal energy and evaporation. Why is that so? Well, the liquid alcohol, okay, gains energy. What kind of energy? Thermal energy, right? Thermal energy. From where? From your skin, right? From your arm, okay? From your skin. And when they have enough energy, they evaporate off. Okay, now since energy is being lost to since your skin or your body loses energy, your body loses energy, or rather it loses thermal energy to the alcohol. Okay, what happens is your skin feels cooler. Alright, so that's the explanation. Pardon my handwriting, it's not easy to write on the tablets here. Okay, so this example actually also tells you that, also reminds us rather that you feel cool not necessarily because the temperature of the object that you are touching is actually cooler than your skin, but rather So long as thermal energy or heat energy is being taken away from your skin or from your body, you will feel the cooling part. So find a metal object around you, right? Let's say your table. If let's say there's metal legs, right? The tables have metal legs. Touch the metal legs. They feel cooler, right? Because energy is being conducted. Chapter 8 is being conducted away from your skin, right? So energy is lost by your skin to the metal. Therefore, you feel that it's cooling, right? But that doesn't mean that the metal is colder than your skin. Why? It may be, right? But doesn't mean that the metal leg is colder than the wooden or the plastic tabletop. Okay, why? Because they are all in room temperature, so they both should be at room temperature, but the metal feels colder than the tabletop, the wood or the plastic tabletop, simply because the metal legs are able to conduct thermal energy from your skin away from you, right, at a faster rate, so your skin feels colder, right, because thermal energy is being lost from your skin. All right, so that's it. This topic, I hope, I mean, there's some overlaps with your chemistry knowledge, probably, right? But I hope it's clear and you have learned something. All right, if not, take care. I'll see you in the next lesson. Take care.